Good day to you all. Today we are going to talk about concurrence theorems in geometry. Now, what do we say or mean when we talk about concurrence theorems? Well, in a triangle, when all the angle bisectors, medians, perpendicular bisectors, and altitudes are connected, each of them intersect at one point, and this point is called the point of concurrency. Now, we will show these on two separate triangles, an obtuse triangle and an acute triangle. Now, let's start with the median. First, let's get the midpoint of each side. Next, we connect them and they all intersect, let's say at point J. Now, the centroid divides each median into a 1:2 ratio. Gj is to Ja is equal to 1:2. Hj is to Jb equals 1:2. And Ij is to Jc is also equal to 1:2. Another noteworthy property is that all the medians connect together at J, and as a result, it creates 6 smaller triangles with equal area. Now let's try this with the acute triangle. So we get the midpoint, the midpoint, the midpoint, and we draw a segment, a segment, a segment. Point N. Now, as I said earlier, Kn is to Nd is 1:2, Ln is to Ne is 1:2, and Mn is to Nf is also 1:2, and Dmn, Mne, Nek, Nkf, NFL, and NLD all have equal area. Okay, let's proceed with the angle bisector. Let me just delete all of these so that we could show the special properties of angle bisectors in a triangle. So we draw angle bisector of B, the angle bisector of A, and the angle bisector of C. And now they all connect or intersect at one point we'll call G. G is called the incenter of the triangle. Now, what are the special properties of the incenter? Well, it is equidistant to all of the sides. Let me show you why. So when we draw perpendiculars from G to AC, G to BC, and G to AB, and we draw points this, and this. When we connect all of these points through a circle, we get something called as the incircle. So G is the center of this so-called incircle, and GH, GI, and GJ are all the in radii. The singular form is in radius. So again, the special property of angle bisectors is that it connects at a common point called the incenter, and it is equidistant to all sides. Now let's show this in the acute triangle. So we draw the angle bisectors. We draw the angle bisectors here, here, here. The angle bisector of F and the angle bisector of E. And they all intersect at point K. Next, we draw the perpendiculars to each side. and we name all the points that intersect it. Now, let us connect these 3 points using a circle. Now, this is the in circle. I also forgot to mention that the in circle is the largest circle that you can fit inside the triangle. So, from the figure, we can see that KL is equal to KM is equal to KN because these are all radii. Moving on to the next concurrence theorem is the perpendicular bisector. Now, we draw perpendicular bisectors here, here, and here. It is possible that the perpendicular bisector can be inside the triangle, outside the triangle, or on the triangle itself. Now, let this point be G. And now, when we connect this point G to all of the vertices of the triangle, these are all equal. These are all equal. I can prove it to you by showing the measure. See? GA is 10.4, GB is 10.4, and GC is 10.4. When you connect all the three vertices, it creates the circumcircle. Now, G is the circumcenter of this circumcircle. A circumcircle is basically a circle that goes through all the points of the triangle. And point G is the center. Point G is the center of this circle. Now, the theorem for perpendicular bisector is that the circumcenter is always equidistant to all of the vertices of the triangle. Now let us try this on the acute triangle. Perpendicular bisector here, here, and here. And they connect at point H. So H is now inside the triangle. Then we connect all the vertices through a circle, and H is now the circumcenter of this circumcircle. So when we draw segments HD, HE, and HF, these are all equidistant. To show you again, here, 9.6, 9.6, and 9.6. So that's a very noteworthy property of perpendicular bisectors. Moving on to the orthocenter. So, to draw the orthocenter, we need to draw all the altitudes first. So, from point A to point BC such that it's perpendicular, B to AC in the same way, and C to AB. Also, it is possible that the orthocenters may be inside, on, or outside the triangle. Now, let's call this point G. There isn't really a special property to an orthocenter. There isn't really anything noteworthy about an orthocenter. It's just that it's the intersection of all the altitudes of the triangle. But when we connect it to an acute triangle, D perpendicular to EF, E perpendicular to DF, and F perpendicular to DE, and let this be point H. This constructs 6 right triangles, not necessarily with equal area. Anyways, that is all for today. I'm sorry if I wasn't really good at explaining anything. This is the first time I made a video about math, and I hope it really helped. I'll try to explain it better this next time, and um for the next video I'll show you why these special properties are actually true. So thank you, that's it, and goodbye.